Okay. So, the goal was to give a sort of a scattered, intentionally scattered samplings of some of the canonical widely studied questions, easy to relate to questions that have been the bread and butter of game theory. So, and in particular the emphasis was on this algorithmic aspects of game theory. You have seen quite a few algorithms actually, and this doesn't quite stop here, and you will see tomorrow. I will just give a brief preview of what is coming tomorrow. For the first 2 lectures tomorrow, you will see what is computation algorithmically attainable. We have a very formal notion of what is computationally or algorithmically attainable in this realm of questions, and what is not. So, the sort of there is a separating line. Okay. So, this particular topic, routing and congestion games, has been is sort of let us see, if I told you, but now you know what a game is, right. It is basically interaction between entities where the precise behavior at any given point cannot be precisely determined. If it could be, then we would just put it in an input, the standard kind of a thing, and just compute an optimization question from it, right, or a feasibility question. But the fact is that that there are certain unknowns, how certain entities will behave, maybe just as to guarantee their best outcome, as well as in response to other people, we have these additional complications that we have been looking at. Okay. So, if I told you to think about games in the wild, like certain natural phenomena where you observe this sort of thing, what would come to your mind? Like, could you give an example? So, as opposed to like the auction scenario or those matching markets and so on and so forth, right? Those are fabricated by us. But if I were to ask you, just tell me an example of something that you see out in nature, a game type setup, what would that be? Traffic. It was a very leading question. I know, yeah, exactly. So, I tried to find the most congested road network, the picture which was also had good resolution, and this is the one that sort of seemed to fit the bill. So, you have all this sort of you have what, 2-lane highway, I don't know, there are actually 4-lane highways, there is a divider in between, there are overpasses and so on and so forth. And there was another picture of a different version of that, where you see this entire like a portion of this traffic and this one meeting somewhere. Okay. I couldn't manage to get all those pictures here. So, what exactly is happening here? It seems like it is a rush hour traffic on a highway where people are all trying to get to work, lots of cars, buses, jockeying for space. Now, you live where you live and you work where you work, right. So, sometimes it is unavoidable, you have to take certain crowded crowded the roads at certain times of the day. So, now the question naturally is, so what should be, so obviously it is over here, what is my goal? To get to a place A to B as quickly as possible. It is not one of those scenes where the journey is the objective and you do not care when you get to it. It is not one of those things. Think about precisely, you want to get to a place fast, right. Okay. So, you must have, so I will just briefly ask you to think about this. When I am just looking at point A to point, like all these points on the map, and I see the distances on the map, I have a very clear idea, precise idea of which is the shortest route from A to B, right. And you know algorithmic approaches to solve this question very formally with precise proof and time complexity argument, right. That is a standard optimization type of scenario. Now, but when I have to actually travel on that route, and when I know there are other people, especially when there is traffic involved, and I do not know how people are deciding, how many people, I can make some assumptions based on my personal experience, this time of the day, this day of the week, blah, 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 but I do not know exactly how many people would be on the road at any given time. Then the calculation of time, shortest route is different. It is no longer a distance based measure, or distance does not directly correlate to time, correct. So, that is the difference. This is a very classic simple example of seeing how standard optimization differs from game theoretic scenarios. So, this is like playing a game between strategic agents. All of these are agents and they are all trying to get to point A to point B, whatever. I mean, they might have different destination and source and destination and so on and so on, but they are using a common shared resource, which is the road. That is the thing. Again, in a certain way, this is also a resource allocation problem that you saw. I mean, you saw other resource allocation problem in terms of matching and so on. This is also a sort of a resource sharing problem. Here, everybody can share this thing as long as they can use it and so on and so forth. And the question is, it is in all of our interest to use it in a way so that it sort of minimizes everybody's time, right. But how to do that together without a overarching entity telling us exactly what to do? That is the problem. Is it clear? Okay. So, unsurprisingly, road networks have been around for hundreds and hundreds of years. Scientists have traveled, have studied congestion, traffic patterns and so on and so forth. The subject of transportation, engineering and so on has been very old and so on and so forth. So, this gentleman by the name of Pigou studied the most simplest form of sort of road network in 1920, and his setup was the following. You have point A to another point B, you have these two roads. Okay. One road, this road has a cost function. Cost is traffic delay. Okay. So, I am going to use the word cost simply because this is a quantity you want to minimize, time of travel. So, if you put x unit of flow through this traffic flow, this is going to take sort of linear that much amount of time. This on the other hand is a peculiar road that no matter how much amount of traffic you push through this, it is always going to take unit 1. So, you can look at it as like 1 hour. Okay. It is not a particularly good this thing, but think of it as like time also as being unit, traffic also as being unit, it will sort of make sense more. Okay. So, what is it that if I wanted to push 1 unit of flow through this unit of traffic, I will use the word flow and traffic interchangeably, you will see later, basically it is just a way of phrasing things. What should I do? What should be my, or rather, is there a dominant strategy here? You recall what a dominant strategy is? Sorry?
Any other strategy would be worse.
No matter what others.
No matter what others.
Yes. And what is the difference between that first thing that you were saying and this one?
That was the Nash.
Sorry? Say?
That was the Nash. That I would be worse off if I did anything else.
Okay. Yes, assuming others are doing exactly the same and so on. There are lots of caveats thrown in because it is not exactly clear what it means to be best among all. Okay, that is a nuanced sort of thing. So, yeah, so dominant strategy is the best course of action I can adopt no matter what others are doing. Okay. All right. So, over here what should be the dominant strategy for any person? I am leaving early in the morning, what should I do? Cx equal to 1?
Both.
See, but Cx equal to 1 is saying even if I am the one traveling on this thing, right, and everybody else is taking the other path, I am still going to take 1 hour, even though if I had taken this, if the situation was reverse, like I was actually going to take this and all others were pushed through here, this would take literally 1 unit of time.
This one and that one is different.
Yes, this is okay. So, let us try to understand what I am trying to say here. Okay, this is saying there is 1 unit of traffic. Think in fractional terms. If you send half unit of traffic, okay, half unit of flow, you will basically take half of whatever time it would otherwise take. Okay. So, we just talk in fractions, so just so that the numbers sort of make sense. Okay. You can scale it up by hours, minutes, whatever you want. This is basically suggesting a constant amount of time, irrespective of amount of flow. So, this constant, this cost function is basically a constant function. This is traffic dependent or load dependent.
So see, no one was on that road. So how much? Say here I will take 1 hour. So there, what amount of time will I take? If no one was there, only I was there.
I would take, think about me being one, this thing, I would take literally whatever my time is. So, okay, so this is a bit, okay, I understand what confusion is. Think about this as being 100 people traveling, okay. This is some, instead of 1, take this as like 1000, this, okay, 100. Let's take 80, okay. Let's take this to be 80. This is 100, 100 cars are traveling. This would be, if I was the only person on the road, I would basically reach in 1 minute. One person takes 1 unit amount of time to reach. That's how you interpret it, okay. Okay. So now, so the mental picture you have to have is, this is not load dependent.
Yes.
This costs you a certain amount of time irrespective of how many people are on the road. This on the other hand is load specific.
So I was thinking C of 1 is equal to 1 there. So both.
Yes, I know, I understand this thing. So think about 1 unit of traffic, x being fractional value. Okay? So that way.
No, why don't we just take Cx equal to x and Cx equal to 1000 or...
Yes.
Yeah, that's what I was saying. I just tried to
fix
change
the
the example. This thing. Think about as this being a large number. Okay? A large number, but still, if this is, it should still make sense that if everybody is on this road, then basically everybody pays the same amount.
Yeah, so I'm saying C of x equal to 1000 and that is C of x equal to x.
X.
So if I'm the first person,
Yeah.
then I only take
Yes.
1 unit of time.
Yeah.
Up to 999 is best that
Yes.
I use the first path.
So let's say this Cx equal to 1 is to be interpreted as some large constant, okay? So let's see 1000. Okay. So this way, and Cx is, the other one is.
Like you should use the function C1x and C2x.
So the point is, there is one cost on the edges of the graph, okay? Positive cost, negative cost doesn't make sense when it comes to traffic. It's like, it can't be that you have non-decreasing values, right? So yeah, so C is basically 2 different values, okay? So this is one edge, this is the other edge, okay? All right. So if I told you, if I have no idea what other people are doing, I'm just thinking about myself. Taking this is no worse than taking this. Actually, this is why I chose this to be the value, because if all of 1 unit of flow was flowing this path would take exactly same amount of time as this path. But if there was lesser flow on this path, then it would take less time. So this path for me as an individual is at least as good as this. Okay, this is why I sort of took this, okay, because I'm saying 1 unit flow and so on. Is this clear?
But then you are always considering that path, the number of cars won't exceed say 1000.
No, over here we are assuming as if there is a amount of volume of traffic that will start from A is known, and I am assuming that to be like 1, and I am going to fractionalize it, half of it going here, 1/3, you can argue it that way, okay. It's like this is the volume, whatever it is, 100 cars, 1000 cars, whatever, but we'll talk in terms of fraction. That
in worst case both are same.
yes, right, that's the idea. If everybody were to move through this, it's going to take the same amount of time as this. So when I don't know anything what anybody else is doing, remember you have seen correlated equilibria and other notions of equilibria. Here I have no idea what others are doing. This is why the definition is irrespective of what others are doing. Taking this route is no worse than taking this. So that's the dominant strategy. Okay. So what is the expected time of travel here? Okay, when I say expected time, I am just saying everybody, like total time of traffic flowing from A to B. This is basically the amount you multiply how each person takes this much traffic, this much amount of time. So all of them together, it will take 1 unit, right? Okay. Now, is this the best we can do, or is there a better outcome? there's a department of police which manages traffic. They monitor all these things. So is there something that they can do, let's say, that, how would I divert?
If a certain number of cars have gone to that side,
Okay.
let's say 100 cars have gone to that side, so 101 car should go to this.
Okay, so this is why we are talking in terms of fraction. You don't know how many cars are actually, let's say, going to start, right? So what we can say is how much percentage of flow can we move through this path and how much to divert through here. That way the calculation does not become number of cars specific. If we are talking in terms of volume then. So how much, what do you think could be a good diversion strategy here?
But others would be worse off.
Half, let's try half, right? Okay,
But
yeah.
they would be worse off.
But right now, everybody is trying to go this, right? Everybody is taking the same amount of time. Now we are trying to see, let's see, can we do better? So he is suggesting, let's see half and half. If I push half amount of flow here, right, the load on this edge reduces. So these people will reach faster. Yes, this is why I said traffic control. I am not doing it because I have determined this is, I am going to stick to it. This is the difference between dominant strategy and other better solution concepts, right. But there is a way where at least some people will be better off, particularly those people who are not, right, after the movement of this half and half. How much would be now the time travel by like total time taken by people whoever started from A to reach B?
0.5 for the above and 1 for the lower.
Yes. So it's half times half, right? Half of the volume going there. Let's say Metro Goldwyn Mayer movie. Okay. All right. So yes. So this is the. Do you agree? It is 3/4. When we say 1 unit of traffic, we are saying whatever amount of flow is coming through, I am just going to route half of it this way, half of it that way.
I mean,
This is why I wrote here 1 unit of traffic.
so look at the first thing, right? It has become half times half.
Yes. And this is half people flowing, but each one will still take 1 unit 1 time.
So like, at least the way you wrote it up, set it up, it appears that the first path should act bad some point of time, right?
Which was part? The top part.
Top path.
The top part is fully congested when
But
everybody
when
is
it's
flowing.
congested, I'm taking less time there, right?
Yes, so this is true. Now people who are on the first part are taking half times half, 1/4 amount of time. Previously they were all taking
Then, like,
1.
yeah, so like that's best that everybody just goes to the top.
Then the congestion will be more.
The congestion will be, just see, no, these, think. Previously everybody was taking this path, right? Everybody was taking this path. Nobody was taking this path. So the amount of time people would have taken to go via this, everybody is actually the same as everybody now traveling through this. Now we are trying to shift some of the load to another path. So this road is now less congested. So traffic can flow faster on this. And the people who have moved on to, have been moved, let's call it, like have been forced onto this path, they are now taking whatever the precise fixed overhead is. But the gain is, this is why the goal is here to minimize the total time taken for flow to move through the network. So because the reduction of traffic or congestion on the first path brings down the travel time of people on the first path. That's what is reflected here. Yes,
If you
this
change the value C equal to 1 to large,
this will change depending on how much volume. So this is the Cx, let's say amount of traffic flowing dex times Cx. Whatever you will see an example. This is basically the volume of traffic, half of it is flowing and the Cx is this thing. So if you put a different Cx, of course the value will change and we'll see an example how, yes.
Fraction
we take, it gives less than 1 time, right? Whatever fraction between, let's say we take value 1/4 and 3/4.
Yes.
That will also give me less than 1 time, 1 unit of time.
Yes, and what does that say? That reducing congestion on the top edge actually gives you better travel time.
In any way.
Yes, and he suggested half. I was thinking of half. So this is it. Okay. What just a second? Is it clear that there would be a reduction the moment I move some traffic from the first part, because those people, they are experiencing less congestion, so they will be able to travel faster. Okay, that's where the advantage comes in. Yes.
So this is dominant strategy in terms of traffic control police.
Yes.
But in terms of passengers, it is like one group of passengers having.
The dominant strategy is defined in terms of what an agent can do, irrespective of what others are doing. Here, agents are people traveling on the road, cars on the road. This is the unique dominant strategy here. That thing that we have, that's a fabricated, that's one possible flow of traffic through the network. So now the question is, the outcome obtained by dominant strategy is inferior to another outcome in which some flow can be moved on to other paths. Correct? Now, I am asking now your question, the socially beneficial outcome is what? The traffic police or the traffic control does not care about how fast you are getting from point A to point B. What they care about is the total time travel for all people concerned on the road, right? So, from that perspective, that's the social optimum. What is the best possible way of rerouting traffic so that everybody across the board sees a improvement in their travel time? Okay? So, that's the sort of thing that we are actually driving towards in this situation.
We are not looking for fairness or anything.
No. Fairness here, this is why fairness is very context specific. Fairness here is from the social, like everybody's perspective taken together, not an individual. There is no guarantee who gets moved from here to here. Okay? So, this is the socially fair outcome, this sort of a redistribution of traffic. Okay? All right. So, I have already said what should be the social goal. Naturally, for traffic control at least, it should be reduction in travel time across the board, right? Okay. So, how do we formalize this? Any idea?
Ma'am, the domain is between 0 to 1. I mean that x.
Yes.
Okay. So can we convert that to an equation?
Sorry?
We can just convert that to an equation.
We can convert it into equation. What does that mean?
Equation. Formulation.
Assign some fraction to the first edge and rest of the fraction would go to the second edge, right? And then find the minimum of that
Yes.
expected value, which is half.
Yes. In this particular situation, half and half is the best outcome you can, and that can be derived mathematically. Like if you try to do redistribution in terms of a little bit more there, little less there, you don't get a better outcome. Half and half is really the best possible outcome. So, therefore, we say, let us just go to this thing 1 second. So, this is the idealized socially beneficial outcome, this thing, 3/4 is like the guaranteed thing, right? So, it is like 25% reduction in travel time compared to this. That is how we interpret this, correct? Okay. So, we agree that the social objective here, there can be many different objectives, but for the purpose of this talk, the socially beneficial objective is to minimize average travel time, right? Actually, I am saying average, but it is basically cumulative. Its average makes sense here because you are dividing by 1, you know, like the whole volume of traffic, so it is average, but the calculation here you can also cumulatively you can say, okay. So, how can we make this, so how far given, so what I am asking you, can we make this precise, that how far can we be away from the socially optimum solution? how do I capture this? That here is a situation. If you were looking at road traffic pattern, here is a situation. You know what is the idealized outcome is. You can do some math, right? And now you're trying to understand how far am I from that. Is there a way to mathematically capture it?
Find the difference in cost.
Sorry?
Find the difference in cumulative cost of this as well. In this
Okay, difference is one. Anything else?
ratio.
Ratio. So, ratio makes more sense here because again, we are not talking about 10. See, the amount of time 100 cars flowing through traffic would versus 1000, obviously the number would be different, right? But the ratio basically tells us a relative difference. So, ratio here makes more sense in that way. So, there the definition here is this thing called price of anarchy. So, in this particular context, this game, price of anarchy is measured as travel time in this dominant strategy equilibrium divided by minimum possible average travel time. Okay? So, why am I using the numerator as if the worst possible outcome, worst possible traffic behavior is attained in a dominant strategy?
The case that we were doing the
definition makes sense for any network, right?
like dominant strategy will always be the worst one.
I am asking, is it or is it a reasonable way of capturing worst possible behavior? So, I said this at the very first class. Dominant strategy is our way of understanding the selfish behavior, like a person who is entirely focused on themselves and trying to come up with a strategy that works for them as well as anything else. Correct? Now, such a strategy may not always exist. We have seen a lot of examples where in games a dominant strategy does not exist. Be that as it may, but in situations where it does exist, it tells us very precisely what the precise behavior will be of rational agents behaving or acting completely independently, right? All these were sort of things that I sort of asked you all to think about in the first class. So, all of that is sort of coming together. This is why dominant strategy, the travel time in a dominant strategy, right, which exists here is the way to capture worst possible behavior. And a social benefit, socially optimum behavior, socially optimum outcome is of course the minimizing the average travel time. Okay? So, this is this thing called price of anarchy. So, in our example, what is the price of anarchy? Right, just let us run out the calculation, it is 4 by 3, right, 1 by 3/4 and so 4 by 3. Okay. So, now Pallavi asked, clear so far?
This is one shot game, right? 0.5 single simultaneously. So
Yeah.
like
I mean, you could call, I mean, it does not have to be simulated, like the traffic could be that, okay, we will push half now and then in the next step we push half, but the gameplay is knowing how to split the flow.
like this
It does not have to be like a simultaneous game.
Like could this be thought as cooperative game where say the traffic, they agree that half of us will go here, half of us will go here randomly from a dice.
If such a thing could be done where people can actually coordinate it among each other, it could be. But the point is they don't. If they did, we would not actually need perhaps traffic police.
I just on A, I put up something. First car comes, I tell you without knowing anything which paths to go. If it is odd object, I send you here. It is even object, I send you somewhere
So
else.
you are talking about implementation. So as I was answering in, there might be multiple way of implementing this socially optimum outcome. That is a different question. That's infrastructure question as to how do you, I mean, manage, get to this idealized outcome. Okay, like where to put what kind of traffic control to put. But what I am trying to say is, first and foremost, before I put in any measures on the road, I first have to know what is the outcome what is the goal that I am trying to get to. Here the goal we agree is to route half amount of flow on this path, like if there is 1 unit volume of flow going through, half should go there and half should go here. That is all. How we implement that, I am not talking about. Okay. All right. So, what if the cost is non-linear, right? Take P to be very large. So, this is like a very high congestion path. Just a little bit of amount of flow you have, the delay is very high. Okay? And this is again the same thing. It is almost like constant time travel path. Sorry? Yes, but still it is half, and this sort of thing, like the cost increases. If you throw unit half amount of flow, then the cost experienced by that person would be half to the power p. Okay? All right. Now, so what do you think will happen here? This still remains the dominant strategy for the same logic. I do not know what others are doing. I am just going to go this. When x is 1, basically everybody is taking this path is no worse than taking this path. Therefore, I might as well take this path, no matter what others are doing, right. So, everybody acting independently, no coordination, that would again be the dominant strategy. Okay. What would be the optimum social strategy?
It will happen at pth root of 1 by p plus.
Okay. There is a value at which the idealized outcome would be attained. Yes. However, let us think of it more sort of like a thought experiment. Like if I were as a person trying to simulate this sort of thing, I would think, well, I am trying to reduce congestion from here. Everybody is now going through this. Think of me as being epsilon by epsilon, I am going to move the traffic from here to here, and let us see how the values change. Okay. So, initially it was 1 over there. Now, I have moved epsilon amount of flow, which is very small, epsilon is a fraction again, to this path, correct. So, what should be now the travel time? Average travel time?
Epsilon plus 1 minus epsilon times x2.
Okay. Yeah. Yes. So, it is the same kind of calculation. Epsilon is the volume of flow going through here, the cost function is 1, this is the volume going through here, and this is the cost function on this path, right? Yes.
I don't understand why you're doing with this epsilon little goes here. I mean, why, as they are saying, why can't we just compute the function, decide what is the best strategy?
I'm trying to say that it can be, that the value can be very bad. Just hold on, we'll see. Okay? So this. If in your calculation, if p is very large, what does that number tend to? Exactly. The number he said, when p is very large, it tends to 0. That's all that matters to me. You will see why. Okay. So here also you can see that if p is very large, epsilon being small, this sort of term dominates over this, right? So what should be the price of anarchy? This value basically tends to 0. Price of anarchy would be, this is again the behavior, the worst possible selfish behavior. There is some value of epsilon for which that actually actualizes the optimum social welfare, right. But regardless of what that precise value of epsilon is, if p is very large, the value tends to 0, right. So, it is like, oh, people are really traveling fast, right. So, what does this mean? The bad behavior is so far from the idealized outcome. So, price of anarchy is very high, in fact, it is unbounded. Is it clear? What just happened?
But then you are assuming that like this x power p, like
p is very large, yes, I am assuming that. That is why I am saying I am giving a cost function, a non-linear cost function. So, when the cost function was linear, we got in this very simple network, the price of anarchy is 4/3. It is a bounded quantity, right. Ideal situation, okay, tell me something before I, what should be the value of price of anarchy? It is a ratio, right. Is it less than 1, greater than 1, what, at least 1, what is it? Greater than equal to 1. Closer I get to 1, it means I am actually getting closer and closer to ideal behavior or ideal outcome. Further away I am from 1, the situation is very chaotic, That is why anarchy. Okay. So, I am talking about now a road network where the cost function is not linear, that is by definition. I am trying to say, I am giving a very pathological example, let us say, right, that when your P is very large, then you see that that value is basically going to 0. This is excellent traffic control, excellent traffic management. The problem is, it just means that the selfish behavior of people, like the uncontrolled situation, would be very far from the idealized situation, which is what price of anarchy tries to capture.
Here P being very large, meaning that we are going very like that route is very fast already, right?
Yes. Yes. But what happened? Everybody going through this does not. If everybody starts going to this, then nobody sees the benefit.
Only little bit if we should.
Yes, that's the idea. That if, because everybody is taking this thing, this is a very fast route, but nobody sees any benefit. Shifting flow, shifting some amount of traffic, even if it is very small as epsilon, sees an appreciable improvement. And when P is so large enough, it's a drastic improvement. That's the point. Okay. Okay, that answers your question, right? This was just a calculation in terms of this thing. Okay.
Understand the intuition. So P is very large. If one person is moving, let's say 1 unit of time they are taking.
It's not like that. It's not that way. This cost function is a function of the volume of flow. So we are assuming, suppose when we say 1 unit, doesn't mean 1 car. It means whatever, 1,000, maybe hundreds of cars, of which if I just each individual, like whatever the volume is, like if half of it were to go on this path, it would take half to the power P. Each individual, so each individual, see, when I am in traffic, I am experiencing delay because of the presence of those other people, right? Everybody who is on with me on that road is experiencing traffic because of all of us, correct? That's the idea. So if you send half amount of flow, this is the flow, but each person is experiencing this much amount of delay because of the presence of all these people.
For one person, the X would be say 1,000 cars, then 1 by 1,000.
Yes,
So that would
this
be
is the thing. That would be
0.001.
like, if you say, suppose you say X unit of flow is going, then it will be something like 1 by X. Okay, this is why. Alright, so now let's observe something. So we agree that even for simple networks, as simple as this, just source and this thing, having non-linear delay function can make the situation very bad, right? Correct? Alright. Suppose I have a slightly more complicated network. You have these hops, okay? It's basically a Pigo with a few more these things in the middle. So you interpret the same thing from here O to V. It takes this amount of linear amount of flow, a linear amount of delay. This is again a constant delay path and so on, okay? Here, what is again the dominant strategy?
There is
Like alternatively taking.
Alternatively, I am only going to travel once.
OVD is the
Yeah, it's like symmetric, right? I can see that this is this. I as an individual, if I go take this, this is at least as good as taking this. When I am starting off, I see that this is at least as good as taking this. Of course, when I get here, then again the delay is this thing. So basically I see this path and this path basically is the same thing for me as an individual. So as a dominant strategy argument, taking any one of these paths would be the same thing, right? However, if half people and half people go there, then what would be the traffic, what would be the travel time?
Half into 1, 3 by 4 into 2.
Yes. So again, this half times half, plus half, right, and twice of that, because you have now 2 paths to go via. Okay, all right. Now imagine here people did not have, because this literally this O to D and O to D via V and W is exactly the same for me. Now if the city government decides to build a super fast highway, which takes, let's say it's so fast, it's almost as teleportation, like you can get in 0 amount of time, the best possible. Okay, this is a thought experiment, as fast as possibly can. Then what happens? What is the dominant strategy now? Correct. Why is taking this road always going to be part of the dominant strategy? Right, I am as a person thinking, if I am going to go this to this, this and this are the same as before, if this did not exist. Now because this exists, I might as well just take this. It cannot be worse for me than keep on traveling like this, correct? Right? Okay. And now everybody wants to take that path. So now what happens to the congestion? It gets worse, even though they have built a super highway. And this is exactly what happens in lot of cities.
But time required would be less than this.
Why? Why? Yes, because everybody is now going there. There is no split. Here, at least some people may have decided, I might as well take this, independent, because I am seeing both things are different. It just so happens some of us decided to take this. Both of our people on both sides of the street will sort of enjoy like a shortened travel time. But over here, that existence of that super highway makes things absolutely like everybody is thinking of the targeting that one. And so again, we are back to that Pigot style congestion, right? So this thing would be this. Everybody is traveling through this. This is 0, but this is whole thing. Again, see a whole volume of traffic is going through. So now I am experiencing travel time of 2. Correct? So what is the price of anarchy here? 2 by 3 by 2, right? Yeah, 4 by 3 again, right?
Yes.
Okay, so remember this. This actually. Okay. Tell me, what is the socially beneficial outcome when this thing actually exists? Huh? Even when this path exists, a beneficial routing would be, a better routing would still be to move half here, half here. This then becomes the optimum social the outcome, even when you have this path, the superhighway in the middle. Okay, so there is one picture missing probably. Yeah, so imagine this, which was a dominant strategy in this situation becomes the optimum routing strategy in the presence of the superhighway. Correct? All right.
What if half of the people go for take OVWD and then half take OWD?
OVWD, half. But then some people are coming through here also, right? There will be congestion here.
But they will leave before that.
That's not good to have. Okay, but okay, we don't think about in real time traffic, this sort of thing, those sorts of things would be taken in, but this is a simplified analysis. So that's the issue here. This path, if I allow traffic to come through from here as well as here, this path will become very congested, and that will lead to the overall time delay. This is why keeping flows as split as possible is the best. That is the picture I was trying to find, like where, like you have a confluence of traffic coming from very many directions. It happens on road crossings, obviously, we have all seen. Yes, good point. Yes, I didn't mention that. There, inadvertently, dominant strategy is also the socially optimum outcome, right? So here, if in this network, the price of anarchy would be 1.
In this example, can you like say something like government was biased towards the V to W route? Like if they would have made another super highway from W to V, then we could have
yes, maybe,
some kind of.
But then the point, yes, possibly, but I don't know if that actually would be. So this is all this shows is just having shorter roads does not necessarily lead to improved congestion, because now more people will start to take that road, and if that road sort of connects to sort of central location, this increases traffic on those some of those points. That's the idea.
Right? Person will take 1 + 1 2 times. So
that's
it
the
is
other
anyhow
thing.
going to take less time on that route.
Whatever outcome you are going to get by giving a double pass like this could be attained just by routing half and half. So the traffic control tries to do this, like this is our road network, we will try to balance as much traffic as possible. Okay. So now what we see is, okay, I still have quite a bit of time. Okay. So let's see, so what is the price of selfish behavior? Over there it was, the best outcome would have been 1, right? It was 4/3. So basically there is a 1/3 cost of selfish behavior, that amounts to 33%, correct? But that is the PIGO type network, that very simple A to B and very simple cost function, linear and so on. Does this situation get worse if you have more complex network? What do you think? It makes sense to ask, right? What if the road's network structure itself is much more complex? You have many more vertices, you have many more roads, you have many more origin and destination pairs, which is generally the case in a city, right? Then it's, what does it think? It should get worse, no?
Probably the traffic will get balanced and so.
How? Is it
with linear cost? If non-linear, we have already shown that it's unbounded.
okay?
Like the example that we saw previously, so the first one, there the dominant strategy and the optimal both were same. So like there was no selfish behavior possible there as such.
Yeah, but that's one example. When we talk about can the situation be worse, we are talking about all possible situations, like worst case analysis, worst case
With non-linear,
consider.
yes.
Sorry?
With non-linear cost function.
We already saw an example how bad it can be, right? So when you have to establish something being bad, one example is good enough. But if you have to argue against it can never be bad, that's a more general argument, right? Okay, so let's say linear cost only. But the network is complex. What happens then?
So we have to bound the PO.
Yes.
What do you mean by more complex?
More vertices, more edges, overlapping, shorter, like the whatever network we saw, this is like, it's 2 vertex, 2 paths and so on and so forth. Just imagine, think of any graph, like think about your road network, like your city road structure, look at a map, how much more complex it is, right?
One thing we can do is have a bigger network and then like join them together.
But you don't get to decide the network, it's the network is what it is, like city the roads.
Yeah.
Now we are saying, can it get worse? You are saying, if I stitch bunch of PIGO networks together, then I'll get bad behavior?
Yes, the POI will be like high.
Even for linear cost?
Yes.
Okay, I see. So that's, you're trying to give an example where it can be actually bad by doing this this thing. Okay. Any other suggestion? This is a natural question to ask, right? Like, how bad can it be? There's one.
Yeah, if there are many roads, maybe say only two vertices, but many roads, one is constant, another are like x, 2x, 3x, then all of them will take only the least one, and that would again give the first.
How bad? But your what was the cost function? It was not linear, correct? Linear. Okay. What was the type of cost function you were saying? You said you have all these this sort of rows, right?
Yeah, so x, 2x and 1.
X, 2x and 1.
But what,
How bad can this be?
what if we do xx instead of 2x?
You tell me how bad this will be. Okay, you find the POA of this. What are you saying?
Like both are x.
So that will be like the Braze thing, right? The Braze network, right? Because over there you had a 2-hop this thing, but basically you can come this thing and the same thing happened, right? Yeah. So the Braze wala was also 4/3, right? The same thing as Pico. It's a slightly more complex network, right? Where you have more vertices, but it's still 4/3. But those are very simple networks, and you will calculate this and try to tell me, okay, what this value is. It's a good thing to try and see. So we agree that this is a very reasonable question to ask. How bad can the price of anarchy be, right? The worst possible. Okay, for a road network of the kind that we are thinking, I can see the distance traveled and the cost associated. So I can at any time compute what would be the best possible outcome for me versus that. That solution exists for any given map, for a given sort of road network. That's a good question, right? A given road network, but it's a given thing. You can see that if I take this route or this route, what would be my travel time? And I'm thinking of irrespective. So in this situation, dominant strategy always exists. Okay. So now we have some time, so I'm just going to tell you something. Why I like this topic so much, and why this has become why this is such a celebrated work. What I'm going to tell you next. This sort of perspective that we are talking about so freely and easily, that what is the worst kind of behavior a road network can sort of exhibit. It's the sort of question that somehow PIGO and scientists, transportation scientists, people studying dynamical systems and so on did not consider for about 80 years, starting from the 1920s. PIGO analyzed that, Braze followed up with Braze network showing that Braze paradox. By the way, that's the thing, it's called Braze paradox. Having a super fast highway does not reduce network traffic. That's what is called the famous Braze paradox. Okay? They studied all these things. Somehow none of them thought to consider what is the worst case behavior. Game theory is a very old subject, much older than algorithm design. Oh, forget algorithm, even theoretical computer science. Theoretical computer science basically became formalized as a subject in the 1960s, in the post-World War period, right, after the Enigma machines and so on, after Turing's thesis came to life. So people have been studying traffic network for a really long time, but they did not think about questions of this worst case behavior, which comes so naturally to theoretical computer scientists, right? Because that's how we measure performance of any system, an algorithm and so on. So this question was not just open, it was unasked. What's the worst possible behavior of a system until the 2002s, early 2000s. Yes, you were saying something?
Like if we forget about minimum travel time for some time, then can we like argue that the time that like the POA is somehow bounded by a function of edges and vertices? Like, is it the right time?
So you are going to completely ignore the cost, traffic cost?
No, just to bound the POA. Is it true that?
What were you saying? It is a function of edges and vertices. What aspect of the edges? It's a function of what?
like number of edges in the network.
Is it just the number of edges? The cost does not matter? So at the very beginning, that's what I said, right? Looking at shortest path between A to B is a static question. It does not, it is a distance question. The distance remains invariant no matter what time of the day you are traveling or when. As long as the road exists, you know what is the distance. But my time of travel differs depending on how much traffic there is on that road. That's the question we are studying. One is a well-known shortest path question you study in basic algorithm design. This is the game theory of traffic control. Okay? So, it cannot be just, even there, we do not have just the number of edges. You could think about shortest path when you have unweighted edges, right? Think about number of edges, that is fine. But the question that we can still answer is, if you have weights on the edges, let us call it like that weights on the edges basically tell us how long that path actually is, and edge represents a road, let us say, right. Not all roads are not of the same length. So, then we can compute the distance. Shortest path is a distance metric. We are talking about shortest time of travel. Okay.
So the question that we are asking is that if networks become more complex, does it imply that?
Does the price of anarchy, so we have seen that when it non-linear, it can be bad. So we are talking about, suppose the cost is linear.
But for say the braces that we saw, that is also linear if you put that super.
Yeah, but that's a very simple network, right?
But there we increased, like we added one more road.
Yes.
With 0.
Yes.
And that made it more complex and it made it more worse.
Why did it make it worse? It is still 4 by 3.
It became 2, right?
But 2 by 2 third. It was
2
by
3 by 2.
Yes.
So it became worse.
But the price of anarchy value remained the same, right?
No, this is.
Right.
Ah, 2 by 3 by 2, 4 by 3.
I used to be able to do this.
Yes.
See? Right? That's the point. The price of in the Bayes network, the dominant strategy solutions value is different. The optimum social value is also different. But the ratio is 4/3 here also. So, I am asking you, just imagine a network which has just much more complex, like you have edges here, you have shortcuts and so on and so forth. And let us say the cost is still linear. Can then we have a worse situation? Yes, because I have built up the question in such a way, the answer has to be no, right? Right. So, the question is the POA does not rise. By the way, we are talking about linear cost, that x to the power p was a non-linear, but there are other cost functions which are like, what do you know, affine, right? You know what is an affine function? So, it is like something like, let us say alpha x plus beta, right. So, linear, when I say linear, I just mean something like this, when I say affine this. That thing where we saw undefined price of anarchy, that is a different sort of thing, this versus x to the power p, right. So, we are now talking about this sort of thing. When you have cost function of this kind and the network is much more complex, it turns out that then also the price of anarchy cannot be worse than 4/3. Okay? And this was a celebrated work by Roughgarden and Eva Tardosh. He was her PhD student. They showed it in 2002, and Roughgarden says, he's recounted this story. He said, I had this result fairly early in my PhD thesis. For the next 6 months, I would go to, he was doing his PhD in Cornell, I would go to their library, which had journals on transportation engineering, dating back almost hundreds of years, and I would look through them. I was thinking, there has to be some paper, some analysis somewhere where people have proved this just in a different kind of way. Okay? because he couldn't believe it that nobody had considered this question, worst case behavior, and it has still to date not been found. So, this is a aspect of perspective. They just were not looking at transportation, they think about average behavior, normal tendencies and all. This thing about measuring your performance of an algorithm or a system against the worst case in the worst possible situation, right? It's one of those contribution to mathematical thinking by theoretical computer scientists. This is our bread and butter. So, this result is what we will see in the, we will see the proof of this. Okay. So, moral of the story, this is unbounded as we saw, but this is a nonlinear function. It turns out that as far as a large class of function, in particular we see affine, okay, the price of anarchy always remains cannot be worse than 4/3. Okay.
Depending on P, is there some bound?
Sorry?
There's some bound dependent on P.
That P?
Yeah. It's
So-
not too large.
Okay. If P is not too large, you can toggle with how much epsilon, how much shift you can give so that you get the best possible. Then it becomes a maxima minima type of a question.
So can you do something like this?
Okay. Yes. Good. All of you are asking all on point questions. We will see a table where we will see this is coming. I screenshotted from the book. There is a table where people have studied different quadratic cost, cubic cost, quintic cost and so on and so forth, and how the value basically rises. So, you can see how with the value of P, how the sort of the trend is. Okay. So, then we come back after a break.
What is the physical intuition for having this x to the power p cost on a road, or like just mathematically, or is there something that we can think of that would happen?
Okay, so this particular function So, this function, if you think of it's basically saying that there is some value p. Okay, so there are people who study this sort of a thing. I mean, there are scientists and engineers who study flow networks, water flow, and so on and so forth, right? Where things this thing. There in their world, there are certain functions, sort of certain functions that pop up, which they observe frequently in nature, because natural systems often will converge to a particular type of behavior, whether they are man-made and so on and so forth. This is not quite from that. This is more like an artificially constructed example where you show that the price of anarchy can be really large. Okay. So, there is no special significance like this is not, I am not claiming that this is the sort of cost traffic load cost that you see in nature. It is not that, but people have studied those sorts of things exist, where people do take real life data, see how certain traffic congestion happens and so on and so forth, and people have plugged in and try to tighten the result, what would be the optimum way of routing costs and so on. This is just sort of to show this worst case behavior. How bad can it be? Well, I will show you an example where the price of anarchy is unbounded.
Is the rough garden whatever theorem is more celebrated because normal roads are linear or affine?
No,
in nature?
rough garden result is celebrated because it says that something as simple as Pigo, just two vertex thing, right? This captures worst case behavior. No matter how complex the road network is and the cost, as long as the cost is affine, this captures worst case behavior. The complexity of the network means nothing. It does not add to the traffic congestion, right? That is what mathematically it means. Now, from a city planning perspective, isn't that a good thing? Because as a city is growing, you can't keep this, I mean the city growth is city growth, it is an organism in and of itself, right. So, road networks will become complex. This at least tells you, as long as we can control the traffic delay on the roads somehow to being affine, we are doing as good as one can, right. That is a reasonable takeaway, right.
Practically the roads that we have, they follow these kind of linear and affine functions?
That I don't know. So this is what I was trying to say. See, this we are talking in terms of road network congestion. This could very well be a network, computer network, right? There, different thing. It could also be a network of water, like pipe network, where fluids are flowing and so on and so forth, right? The word network is a very sort of it's an abstract mathematical way of capturing these sorts of this, and the graph is basically a further mathematical abstraction of that sort of a situation. So I don't, at different situations, different kind of flow is observed. That's what I was trying to say. Certain functions show up more frequently than others. What they are, I don't know. Okay, you can, I'm sure you can check up. And there are scientists who do more sort of fine-tune analysis for those specific networks. But this is just saying, again, worst case behavior, no matter what the situation is. That's the point of mathematics, right? You want to say something as general as possible that is true for as broad a situation as possible. So that's what this says. Specific situations can give you better price of anarchy. All we are saying is it cannot be worse than 4/3. Okay?
In that theorem, we are also assuming that alpha is positive, right?
Yes. Does it make sense for alpha to be negative? Yes. Right? These are common sense sort of this thing. In that table, we basically say this. It's important. Alpha is positive, beta is not negative, and so on and so forth.
Even the beta is negative, state would be increasing function.
Yes, it would be. That's true. But what we want is like, we want a non-decreasing function, naturally. And we want the coefficients to be positive. So coefficient here means this obviously, but you can also think of this as like a coefficient of the 0 order, 0 degree term, like x to the power 0 and so on. True. If this beta could be so large, the magnitude of it, that this one is dwarfed by this. And then having negative makes no sense. Right? Yeah, so but that depends on how alpha, beta together are behaving. Okay.
You're always thinking of x lying between 0 and
Yes, because again this notion of volume. That's the thing. Okay, that's why. We don't want to be talking about this 1,000 cars versus 500 cars. It's just volume of traffic.